We may be living inside a hole in space, 2 billion light-years wide, and for decades, nobody knew it was there. Picture the universe as a sponge, filled with strands of galaxies and gaps of nothing between them. Now picture our entire galaxy sitting inside one of the biggest gaps ever found. Fewer stars, fewer galaxies, emptier than it should be by nearly a third. Astronomers call it the KBC Void, and it stretches so far that light takes 2 billion years to cross it. Today, we travel through this strange hollow region, past a cold patch left over from the birth of the universe, past a monster void where only 60 galaxies drift where thousands belong, and into a mystery that might force scientists to rewrite the laws of gravity itself. If this video is opening your eyes to something you never noticed above you, hit like and subscribe so more of these mysteries find their way to you. Get ready. We start inside the hole. Look up on a clear night, and the sky feels full. Stars everywhere, scattered like sand across black glass. But step back far enough, past our galaxy, past our neighbors, and something strange shows up. Our part of the universe is missing galaxies. Not a few, not a handful lost in the dark, millions of them, gone from where they should be. Astronomers first noticed this by accident. They were counting galaxies the way a park ranger counts trees, sweeping a grid across the sky and tallying every glowing dot. In most directions, the count matched what physics predicted. But around us, the numbers kept coming up short. Fewer galaxies near the Milky Way, fewer bright points scattered nearby, as if someone had scooped out a section of the universe and left our home floating in the gap. At first, scientists assumed it was a mistake. Maybe dust in our own galaxy blocked the view. Maybe the telescopes missed a patch of faint, hard-to-see galaxies, so they checked again and again. They used different telescopes, different wavelengths of light, different teams working on opposite sides of the planet. The gap held up every time. This region has a name now. Scientists call it the KBC Void, and by cosmic standards, it is enormous. It stretches nearly 2 billion light-years across. To picture that, imagine a beam of light, the fastest thing in existence, needing 2 billion years just to cross from one side to the other. Earth is not just near this void. Earth sits inside it. Here is the part that unsettles astronomers the most. The universe is supposed to look roughly the same everywhere, once you zoom out far enough. Clumped in some places, empty in others, but balanced overall, like a sponge with holes and threads spread fairly evenly throughout. That is the basic assumption behind almost every cosmic model built in the last 100 years. A void this size and this deep breaks that assumption in our own cosmic backyard. Some researchers think this could be an ordinary fluctuation, one rare, unlucky patch in an otherwise even universe. Others think it might point to something deeper, a flaw in the equations scientists use to describe how matter spreads out after the Big Bang. Neither side has closed the case yet. What makes this personal is where we are standing. This is not a distant patch of space observed through a telescope aimed at some faraway galaxy cluster. This void surrounds Earth on every side. Every star you have ever seen with your naked eye, every galaxy your phone camera could ever hope to capture, sits inside this same stretch of unusually empty space. For decades, humanity assumed our cosmic address was ordinary, a random, unremarkable spot in a random, unremarkable galaxy. That assumption is now being tested. If the void is real and as strange as some scientists believe, it does not just describe empty space around us. It changes how astronomers measure the entire universe, including how fast it is expanding. To understand how strange this gap truly is, we need to see what first tipped scientists off. Not a missing galaxy, but a mismatch in numbers that never should have appeared. A puzzle buried in the brightness of exploding stars, ready to pull the whole picture apart. Exploding stars do not lie, or so astronomers believed for decades. A certain kind of star death, called a Type 1, a supernova, always burns with close to the same brightness. Astronomers use them like cosmic light bulbs of known wattage. If a supernova looks dimmer than expected, it must be farther away. If it looks brighter, it must be closer. Simple, reliable, trusted for generations. Then the numbers stopped adding up. Researchers comparing supernova brightness across different parts of the sky noticed something odd near our galaxy. The math used to calculate distance and expansion speed kept producing two different answers depending on how far out you measured. Look at supernovas close to home, and the universe seemed to be expanding faster. Look at supernovas from the deep, ancient universe, closer to the beginning of time, and the expansion rate slowed down. This mismatch earned a name that now haunts modern cosmology, the Hubble tension. Picture two rulers measuring the same hallway. One ruler says the hallway is 100 feet long, the other says it is 110 feet long. Both rulers were built carefully, both were tested and checked, yet they refused to agree. That contradiction is exactly what astronomers found when comparing the nearby universe to the ancient, distant one. For years, most scientists assumed the error sat in the measuring tools themselves. Maybe a camera calibration was slightly off, maybe a distance ladder. The chain of measurements astronomers use to calculate how far away something sits had a weak link somewhere in the chain. Teams rebuilt their instruments. They cross-checked with different telescopes. The tension refused to disappear. Then, a new idea entered the conversation. What if the problem was not in the tools, but in the neighborhood? What if Earth simply sits in an unusual pocket of the universe, a region with less matter pulling on nearby galaxies, causing them to drift outward slightly faster than normal? A patch of near emptiness could act like a slight nudge, making our local corner of space appear to expand quicker than the universe as a whole. This idea connected directly back to the missing galaxies scientists had already spotted. If Earth truly sits inside a large, underdense region, both puzzles might share the same root cause. The mismatched ruler and the missing galaxies could be two symptoms of one condition. It is important to be clear about where the science actually stands. This connection remains debated. Some studies support the idea that a giant void could explain the mismatch in expansion speed. Other newer studies, using different techniques, suggest the void may be far smaller than first proposed, too small to fully explain the tension on its own. Nobody has delivered a final answer yet. What began as a strange gap between two brightness measurements has grown into one of the most serious open questions in modern physics. It touches the age of the universe, the fate of the cosmos, and whether our understanding of gravity itself needs revision. And at the center of that question sits Earth, tucked inside a stretch of space that keeps behaving like it does not follow the rules. To understand why this pocket of space matters so much, we need to give it a proper introduction, its size, its shape, and the strange position we hold within it. Every void needs a map, and mapping something invisible is harder than it sounds. You cannot photograph empty space directly. There is nothing there to catch the light. Instead, astronomers had to map the void by tracing its edges, counting where galaxies exist, and noting everywhere they do not. Picture carving a shape out of fog using only the outline of trees still visible around it. That is roughly how scientists built the first models of what became known as the local hole. They plotted galaxy positions across huge sections of sky, layer by layer, distance by distance, until a rough, three-dimensional shape emerged. A shape with far less material inside it than the space surrounding it. The local hole is not perfectly round. Real cosmic voids rarely are. Picture a lumpy, stretched-out bubble, thinner in some directions, wider in others, its edges blurred rather than sharp. Instead of a clean wall, the transition from empty to normal density happens gradually, like fog thinning out the farther you walk from its center. Astronomers first started noticing unusually low galaxy counts near the Milky Way decades ago, well before anyone connected it to a possible explanation for the Hubble tension. Different research groups, using different telescopes and wavelengths of light, kept spotting the same pattern: fewer galaxies close to home compared to regions farther out. Each new survey added another piece to the outline. slowly turning a vague suspicion into a measurable structure. What makes this discovery especially tricky is separating a true, large-scale gap in matter from an ordinary quiet neighborhood, the kind every galaxy might expect to find nearby. Space is not uniform at small scales. Clusters and gaps exist everywhere, similar to how a forest might have a small clearing next to a dense grove of trees. The real question scientists needed to answer was whether Earth's clearing was simply an ordinary clearing or something far larger and far more unusual. Early estimates placed the underdense region at roughly 1 billion light-years in radius, an almost impossible-sounding number for something built from mostly nothing to be an ordinary, expected clearing in the cosmic web, according to standard models. It should have been many times smaller. Instead, survey after survey kept confirming a hole stretching far past what typical structure formation predicts. Confirmed by multiple independent teams, the region around us shows a real, measurable drop in galaxy density compared to farther distances. Still debated exactly how large that drop truly extends and how deep the emptiness goes at its most extreme point. Part of the difficulty comes from Earth's own vantage point. Our galaxy sits close to the flat plane of the Milky Way, a dense band of gas, dust, and stars that blocks huge sections of sky from view, the same way a thick curtain blocks a window. Astronomers call this the zone of avoidance. Any map of the local hole has to work around that blind strip, filling in the missing pieces using statistics and educated estimates rather than direct observation. That gap in coverage is one reason different survey teams sometimes draw the void's outlines slightly differently. This is where the story shifts from simply noticing something strange to actually measuring it properly. To understand how astronomers count galaxies scattered across billions of light-years of space in a survey too vast for any human eye to check by hand, we need to step into the tools and the method that first exposed the gap. Counting stars is impossible. There are simply too many, scattered across distances no human could ever tally by hand. Counting galaxies sounds even harder, since each one contains billions of stars packed together. Yet astronomers have found a way to do exactly that, using light itself as their measuring tool. Think of a massive forest stretching farther than the eye can see. You cannot count every tree individually, but you can count trees carefully inside a small marked section, then use that number to estimate the density across the whole forest. Astronomers use a similar method, called number counting, applied to galaxies instead of trees. They aim telescopes at small, carefully chosen patches of sky and photograph every galaxy visible within that patch, no matter how faint. Then they repeat the process across hundreds of different patches scattered in different directions. Add up the totals, compare the density from one patch to another, and a pattern begins to emerge. Some regions crowded with galaxies, others strangely sparse. The key breakthrough came from switching to near-infrared light instead of ordinary visible light. Infrared light passes through cosmic dust more easily, the same way a flashlight beam cuts through fog better than a dim lantern. Dust clouds in our own galaxy can block and scatter visible light, hiding distant galaxies behind a curtain of debris. Near-infrared light slips past much of that curtain, revealing galaxies that visible light telescopes would have missed entirely. Using this method, one landmark study combined data from multiple sky surveys, cross-referencing infrared brightness with measured distances for hundreds of thousands of galaxies. The team built a three-dimensional density map layer by layer, moving outward from Earth in expanding shells, similar to counting tree density in wider and wider rings, spreading out from a single point in the forest. The results confirmed what smaller studies had hinted at for years. Galaxy density near Earth measured significantly lower than density found much farther away, and this dip did not level off quickly. It persisted across an enormous stretch of space, hundreds of millions of light-years deep, before finally reaching a normal cosmic average. To be clear about the science here, this counting method is well established, and has been repeated by multiple independent research groups using different telescopes. The existence of a real dip in nearby galaxy density is confirmed. What remains actively debated is the exact size, shape, and depth of that dip, since different surveys, using different assumptions and different corrections for incomplete sky coverage, sometimes produce different numbers. One landmark survey behind this discovery covered nearly 90% of the entire sky, an enormous scope for a single project. Reaching that kind of coverage meant combining several separate telescope catalogues into one unified dataset, checking that each instrument measured brightness and distance using compatible standards before the numbers could be safely combined. Only after that careful stitching work could researchers trust the density map that emerged. Covering almost the whole sky mattered enormously, since a survey that only scanned one narrow patch could easily mistake an ordinary local dip for a much larger structure or miss a genuine one entirely by looking the wrong direction. Counting confirmed the gap was real. The next question became far more startling. Just how empty is empty? And how does that number compare to what the rest of the universe normally looks like around any ordinary galaxy? Numbers rarely carry emotional weight on their own. Say a region of space is 20% underdense, and most people's eyes glaze over. But turn that same number into something visual, and it becomes unsettling fast. Imagine a football stadium built to hold 100,000 fans. Now imagine that same stadium sitting nearly a third empty on game day, 30,000 seats sitting untouched, scattered across every section instead of clustered in one corner. That single missing chunk of the crowd is roughly the scale of emptiness astronomers measured when comparing our cosmic neighborhood to the universe at large. Different research teams have reported slightly different numbers, depending on their methods and how far out they measured. Some studies found the region roughly 20% underdense. Others, measuring closer to the center of the gap, found numbers approaching 50% lower than the cosmic average. Even the more conservative estimate describes a hole in the universe unlike almost anything else ever confirmed. To understand why this number troubles scientists so deeply, you have to understand what the universe is supposed to look like on the largest scales. Cosmologists describe the universe using something called the cosmological principle, the idea that if you zoom out far enough, matter spreads out fairly evenly in every direction. Clumps and gaps exist, the same way a sponge has both dense material and empty pockets. But none of those gaps should be too extreme, and none should be too large. A void this deep, spanning close to 2 billion light-years, pushes against that principle harder than almost anything else discovered. Standard models built from decades of observation and mathematics predict small, modest variations in density across large regions of space. They do not comfortably predict a hole this size, this close, right where our own galaxy happens to sit. One team modeling this exact scenario found that the size and depth of the void, when checked against standard cosmological predictions, produced a statistical mismatch exceeding 6 standard deviations. In plain terms, that level of disagreement is treated in physics as essentially impossible to explain through random chance alone. Something about the situation does not fit cleanly into the existing rulebook. It matters to be fair here, because this is where actual scientific debate lives. Not every researcher agrees on how large or how deep the true void really is. A separate study, using a different measuring technique based on tracking the direct motion and distances of nearby galaxies rather than simply counting them, found evidence for a much smaller, underdense region, possibly only a tenth the size originally proposed. Science remains split on exactly how extreme this emptiness truly reaches. Even the disagreement itself teaches something valuable. Two teams, using two different techniques, both aimed at the same patch of sky, and both came back with numbers describing genuine emptiness. They only disagree on the size of that emptiness, not on whether it exists at all. That is a meaningful distinction, because it means the debate is no longer about whether we live somewhere unusual. It is about exactly how unusual that place turns out to be. What everyone agrees on is this: Something measurable, real, and unusual sits around us. The size of that gap changes depending on who you ask and which method they trust most. To understand why that gap even matters at all, we first need to understand what a void actually is, and why calling it empty is more complicated than it sounds. Say the word void, and most people picture total nothingness, a black hole-shaped absence where matter should be but is not. The reality is stranger and, in some ways, more interesting than pure emptiness. Cosmic voids are not vacuum chambers stripped bare of everything inside them. They still contain galaxies, gas, and scattered stars. What makes them voids is not the absence of matter, but a severe shortage of it compared to the busy, crowded regions nearby. Picture a sponge again, its structure built from dense, tangled fibers, with wide open pockets of air trapped between them. Galaxies cluster along the fibers, forming what astronomers call the cosmic web. Voids form the open pockets between those fibers, thin on matter, but never completely bare. Our own local hole follows this same pattern. It still contains galaxies, including our own Milky Way, along with the larger structure it belongs to, called the Laniakea supercluster. What sets this region apart is not zero galaxies, but far fewer galaxies packed into an enormous stretch of space compared to what surrounds it on every side. This distinction matters because it changes how scientists interpret the void's effects. A region with slightly less matter than average still exerts gravity, just less of it than a denser region would. Galaxies inside an underdense region feel a slightly weaker gravitational pull holding them in place, which can cause them to drift outward toward denser regions nearby, similar to marbles slowly rolling away from a shallow dip toward the deeper edges of a bowl. This slow outward drift plays directly into the expansion mismatch scientists have been chasing. If our galaxy sits inside a region with less material tugging on it, nearby galaxies could appear to move away from us slightly faster than galaxies do in denser parts of the universe, simply due to this gentle outward push. That small extra speed could be enough to distort local measurements of how fast the universe is expanding, without actually changing how the universe expands everywhere else. It is worth being precise about what counts as confirmed here. Confirmed, cosmic voids are real, common structures found throughout the universe, and they are never perfectly empty. Confirmed, an underdense region measurably surrounds our galaxy. Still theoretical. Exactly how much that specific regional emptiness contributes to the larger Hubble tension puzzle, since other explanations, involving errors in distance measurement techniques or entirely new physics, remain active possibilities scientists have not ruled out. This sparse rather than empty description also explains why the void took so long to notice in the first place. A truly empty region, with zero galaxies anywhere inside it, would have been obvious from the very first sky surveys ever conducted. A thinly populated region, still containing plenty of galaxies, just spaced farther apart than usual, blends in far more easily, hiding in plain sight until someone counts carefully enough to notice the pattern. Understanding voids as sparse rather than empty reshapes the entire story. This is not a hole punched cleanly through space. It is a thin, stretched-out region, home to fewer galaxies scattered farther apart, sitting inside a much busier cosmic structure. And it turns out our region is far from the only one of its kind. To understand where this particular gap earned its name, we need to meet the scientists who first mapped its edges and gave it a label that stuck. Every major discovery eventually needs a name, and this one came from the scientists who built the clearest map of it yet. In 2013, a team led by researchers Ryan Keenan, Amy Barger, and Lennox Cowie published a detailed study measuring galaxy density using near-infrared light across a huge stretch of the surrounding universe. Their approach combined multiple existing sky surveys into a single, unified dataset, cross-checking galaxy brightness and distance across an enormous portion of the observable sky. Rather than relying on one telescope or one narrow patch of space, they stitched together data covering the vast majority of the visible universe around us, giving their measurement far more weight than smaller, isolated studies that came before it. What they found matched and strengthened earlier hints. A significant underdensity, stretching across hundreds of millions of light years, centered roughly on our own galaxy. Their analysis suggested a region with density measuring around half the cosmic average at its deepest point, a number striking enough that other researchers quickly took notice and began building on the work. The scientific community soon adopted a shorthand name, using the researchers' initials. The KBC Void, standing for Keenan, Barger, and Cowie, became the standard label used across dozens of follow-up papers exploring what this underdense region might mean for cosmology at large. Some researchers alternatively call it the local hole or a local supervoid, depending on the paper and the specific angle being studied. Naming a structure this way might seem like a small detail, but it mattered enormously for the science that followed. A named, well-defined structure gives other researchers something concrete to test, model, and argue about. Instead of vague talk about missing galaxies, scientists now had a specific, citable void with an actual measured density profile, ready to be plugged into equations and compared against theoretical predictions. That is exactly what happened next. Multiple teams began building mathematical models, treating the KBC Void as a real physical structure, then testing whether its size and depth could help explain the ongoing mismatch between local and distant measurements of cosmic expansion. Some of these models found a striking result. A void of roughly this size and depth could, in theory, account for a meaningful chunk of the Hubble tension. Though not necessarily all of it, it is worth staying grounded here. Confirmed, the KBC Void is a real, independently measured structure, published in peer-reviewed research and confirmed by multiple follow-up surveys. Still debated whether it fully explains the expansion mismatch, partially explains it alongside other factors, or turns out to be a smaller contributor than early models suggested. The team's original paper did not set out to solve the Hubble tension at all. Their goal was simpler: mapping galaxy brightness across the sky to study how galaxies evolve over cosmic time. The underdensity showed up almost as a side discovery, an unexpected pattern buried inside data collected for an entirely different purpose. Only years later did other researchers recognize how directly that side discovery connected to the expansion rate puzzle already troubling cosmologists. With a name, a rough shape, and a research trail now established, the next step is grasping just how large this structure truly is. Numbers on a page rarely do justice to something spanning nearly 2 billion light-years. To understand it properly, we need to shrink the universe down to something a human mind can actually picture. 2 billion light-years does not mean anything to most people, and that is not a failure of imagination. It is simply too large a number for a human brain built to judge distances between trees, buildings, and city blocks. To understand the KBC Void, that number needs to shrink down into something a person can actually hold in their mind. Start small. Light travels around 186,000 miles every single second, fast enough to circle Earth about 7.5 times before you finish reading this sentence. In 1 year, light covers about 6 trillion miles. Multiply that by 2 billion, and you get the rough width of the void surrounding our galaxy. That number is still too abstract, so try a different comparison. If the entire observable universe were shrunk down to the size of the United States, stretching coast to coast, the KBC Void alone would cover a stretch equivalent to driving from New York to well past Los Angeles, and then continuing that same drive several times over before finally reaching the void's outer edge. Try another angle. The Milky Way galaxy itself, home to our Sun, our solar system, and every star visible to the naked eye, stretches about 100,000 light-years across. To cross the KBC Void, you would need to line up roughly 20,000 Milky Way galaxies, side by side, edge to edge. in a single unbroken row. Even that comparison struggles to capture the scale, because human minds are not built to process distances this extreme. A better approach is thinking about time instead of distance. Light that started traveling from the far edge of this void 2 billion years ago is only now reaching us. 2 billion years ago on Earth, the most complex life forms were simple, single-celled organisms drifting in ancient oceans. Nothing resembling an animal, a plant, or a tree yet existed. That is how long light has been traveling just across this one structure. Despite spanning a distance that dwarfs any comparison from daily life, the void remains invisible to the naked eye. There is no dark patch to spot in the night sky, no obvious black gap between the stars. Its emptiness only reveals itself through careful counting, careful measurement, and years of painstaking survey work stretched across multiple research teams and telescopes. This is a structure large enough to be measured in billions of years of travel time for light, yet subtle enough to hide from casual observation entirely. Confirmed, its scale, roughly 2 billion light-years across, is well supported by multiple independent surveys. What remains harder to pin down precisely is the exact boundary where the void ends and normal cosmic density begins, since that edge fades gradually, rather than stopping in a sharp, clean line. One more comparison helps drive the scale home. Sunlight takes roughly 5.5 hours to reach Pluto, the outer edge of our solar system. Stretch that same gap out until it matches the width of the KBC Void, and you would need to repeat that 5.5-hour journey more than 3 billion times in a row. Understanding the size answers one question but raises another immediately. If this structure truly surrounds our galaxy on such a massive scale, where exactly does Earth sit within it? Dead center, or somewhere closer to the edge? That question turns out to carry major consequences for how scientists interpret everything the void might be doing to our view of the universe. Position matters enormously in astronomy, and the KBC Void is no exception. Early models assumed Earth sat somewhere near the exact center of this underdense region, the same way a marble might rest near the middle of a shallow bowl. Newer research has complicated that picture in an important way. More recent studies, including analysis published in the past couple of years, suggest our galaxy does not actually sit at the void's center. Instead, we appear to be positioned off to one side, closer to the edge than originally assumed, inside a structure that is neither perfectly smooth nor perfectly symmetrical. Think of a swimming pool with an uneven bottom, deeper on one end and gradually shallower toward the other. If Earth were sitting at the deepest point, we would expect the underdensity to appear roughly equal in every direction we look, the same way water pressure feels consistent from the exact center of a symmetrical pool. Being positioned closer to the shallow end instead means the emptiness should look different depending on which direction you measure, deeper in one direction, shallower in another. This asymmetry actually matters scientifically because it changes the predictions researchers use when testing whether the void could explain the Hubble tension. A perfectly centered galaxy sitting inside a smooth, symmetrical void produces one set of expected effects on local expansion measurements. An off-center galaxy sitting inside a lumpy, uneven void produces a different, messier set of predictions, harder to model cleanly but potentially more realistic given what surveys actually show. Researchers studying this off-center positioning have proposed that the void itself may not have formed as a single smooth depression, but rather as a combination of multiple smaller, underdense regions merging together over billions of years, similar to several shallow depressions in sand gradually blending into one larger, irregular basin as waves smooth the terrain over time. This detail also helps explain why different research teams sometimes report different sizes and depths for the same underlying structure. If you are measuring from a position off to one side rather than dead center, your instruments will naturally pick up different density readings, depending on which direction you point them, even while studying the exact same physical region of space. To stay precise about where the science currently stands, confirmed Multiple studies published within the past 2 years support the idea that our galaxy sits away from the void's true center rather than directly within it. Still theoretical, the exact position, the precise shape of the void's boundary, and how strongly this off-center placement influences local expansion measurements remain active areas of ongoing research and calculation. This off-center placement even affects how scientists interpret the void's edges. Looking toward the deeper side, surveys pick up a steeper, more dramatic drop in galaxy counts. Looking toward the shallow side, that same drop appears gentler and less pronounced. Untangling which readings describe the void's true underlying shape and which simply reflect Earth's specific vantage point within it has become its own careful piece of ongoing detective work. Knowing our position inside this vast structure sets the stage for the void's biggest scientific claim to fame, its potential role in one of the most stubborn disagreements in modern physics. To understand that connection properly, we need to step back and examine the Hubble tension itself, the puzzle that first hinted something unusual might be hiding in our cosmic neighborhood. Every expanding universe needs a speedometer, and cosmologists have one. It is called the Hubble constant, a number describing exactly how fast space itself stretches apart as distance increases. The trouble is, scientists have two different, carefully verified methods for measuring that number, and those two methods refuse to agree. The first method looks backward toward the beginning of time. Scientists study the cosmic microwave background, ancient light left over from shortly after the Big Bang, and use detailed physics models to calculate how fast the universe should be expanding today, based on conditions from billions of years ago. This method consistently produces one specific expansion speed. The second method looks at the nearby universe directly. Scientists measure the distance and speed of relatively close galaxies using tools like pulsating stars with known brightness patterns and exploding stars with predictable light output, then calculate the expansion rate from those direct, local observations. This method consistently produces a different number, noticeably faster than the first. Picture two separate teams calculating the speed of a car using completely different methods. One team calculates speed using a fuel efficiency formula based on how the engine was originally designed. The other team simply clocks the car with a radar gun as it drives past. If both teams did their math correctly, yet keep getting different speeds for the same car, something about the situation itself demands an explanation. This mismatch is not small, and it is not going away with better technology. Scientists have refined both measurement methods repeatedly over the past decade, tightening the margin of error each time. Instead of the gap shrinking as instruments improve, the tension has held steady, and in some analyses grown even more statistically significant. Three broad explanations currently compete for attention. The first suggests a hidden error still exists somewhere in one of the measurement techniques, despite years of careful rechecking. The second suggests new, undiscovered physics might be needed, something missing entirely from current models of how the universe behaves. The third, and the one most connected to our story, suggests our local position in space, sitting inside a large underdense region, could be distorting nearby measurements just enough to create the appearance of faster expansion, without actually representing the true expansion rate of the universe as a whole, being fair to the actual science. None of these three explanations has won a decisive victory yet. Each has published research supporting it, and each has published research challenging it. The Hubble tension remains one of the most actively contested open problems in modern cosmology, discussed at conferences and argued over in journals on a near constant basis. The stakes riding on this disagreement reach far beyond a single number. The expansion rate feeds directly into calculating the age of the universe and the fate awaiting everything within it. Solving the Hubble tension is closer to fixing a cracked foundation running underneath the entire structure of modern cosmology. What makes the void connection so compelling to so many researchers is timing and location. A structure this large, this close, and this well documented, showing up right as scientists search for an explanation for a stubborn measurement gap, is either a remarkable coincidence or a genuine clue hiding in plain sight. To understand how a mostly empty region of space could actually influence something as fundamental as expansion speed, we need to look closer at the physics connecting emptiness to outward motion. Emptiness does not sound like something with the power to fool an entire measurement, yet that is exactly what some cosmologists believe is happening. To understand how, you need to think less like an astronomer for a moment, and more like someone standing at the edge of a hill. Gravity behaves like an invisible net stretched across the universe, tugging matter toward denser regions and away from emptier ones. A galaxy sitting inside an underdense region feels a slightly weaker pull holding it in place compared to a galaxy surrounded by dense clusters on every side. Over billions of years, that weaker pull allows galaxies near the edge of a void to drift outward, gently pulled toward the denser, heavier regions surrounding the emptiness. Now picture Earth sitting inside exactly this kind of situation. If our galaxy sits inside a large, underdense bubble, nearby galaxies within that same bubble would tend to drift outward at a slightly faster pace than galaxies do elsewhere in the universe, simply due to this gentle gravitational imbalance. From our perspective here on Earth, those nearby galaxies would appear to be racing away from us a little faster than expected. Here is the critical part. Scientists calculating the universe's expansion rate using nearby galaxies are essentially clocking how fast those galaxies appear to move away from us. If our local outward drift runs slightly faster than the true, universe-wide average, our calculated expansion speed would come out faster too. Not because the entire universe is actually expanding quicker everywhere, but because our specific corner happens to be caught in an extra outward push. Picture a raft floating gently downstream in a wide, slow-moving river. Now picture that same raft caught briefly in a narrow side channel with a slightly stronger current. Someone timing the raft's speed only during that side channel would clock it moving faster than the river's overall average speed, even though nothing about the river as a whole has actually sped up. This is precisely the mechanism several research teams have proposed and tested using detailed mathematical models. Some of these models successfully reproduce a meaningful chunk of the observed expansion mismatch using a void roughly matching the size and depth of the KBC Void. Other, more recent models using different measurement techniques found evidence for a smaller void, one that would only explain a fraction of the total tension rather than solving it completely on its own. Staying precise about where things currently stand, confirmed, gravity absolutely can create exactly this kind of local outward drift around underdense regions. This is basic, well-tested physics. Still debated whether our specific void is large enough and deep enough to fully explain the entire measured tension, or whether it merely contributes a partial piece toward a larger, still unsolved puzzle involving multiple factors combined together. This raft and river comparison also explains why the effect is so difficult to fully confirm. Anyone measuring the raft's speed needs to know exactly how strong that side channel truly is before calculating how much extra speed it added. Cosmologists need that same precise, agreed-upon measurement of the void's size and depth before they can calculate exactly how much extra drift it adds to our local expansion measurements. If gravity truly is capable of nudging galaxies outward this way, an even bigger question follows close behind. How exactly does gravity behave differently across such an enormous stretch of empty space, and what does that reveal about matter's pull across the largest distances the universe has to offer? Gravity feels simple at small scales. Drop an object, and it falls. Two masses near each other attract, pulling closer together over time. Scale that same basic idea up to the size of galaxies stretched across billions of light years, and the picture becomes far more intricate, involving entire cosmic structures pulling on each other across unimaginable distances. Galaxies do not sit still in space. They drift, carried along by the combined gravitational pull of everything massive surrounding them: distant clusters, superclusters, and enormous filaments of matter stretching across the cosmic web. Scientists call this collective motion peculiar velocity. the extra movement galaxies pick up beyond the basic outward stretch caused by the universe's overall expansion. Recent research measuring this peculiar velocity across our local region has turned up something unusual. Galaxies nearby appear to be flowing outward in a coordinated pattern, moving with a combined bulk speed larger than typical cosmological models predict for a region this size. This coordinated motion is often called a bulk flow, and it behaves almost like an invisible current running through a section of the cosmic ocean. Picture a crowd of people standing in an open field, all facing slightly different directions at first. Now imagine a strong wind begins pushing steadily from one particular side. Over time, that crowd would gradually shift and drift together in the same general direction, carried along by a shared outside force, nudging everyone at once. Galaxies caught inside and around a large void appear to experience something similar, drawn steadily toward the denser, more massive regions surrounding the emptiness. What makes this bulk flow especially puzzling is its behavior at increasing distances. In most models, this kind of coordinated drift should weaken and fade the farther out you measure, similar to ripples spreading outward from a stone dropped in a pond, growing fainter with distance. Instead, several studies measuring this flow found it staying unusually strong, and in some cases even increasing, at distances stretching hundreds of millions of light-years from Earth. This unexpected strength has become its own small mystery inside the larger void story. A modest void producing a modest outward nudge would be relatively easy to explain using standard gravity and standard cosmology. A void producing this much sustained outward motion, stretching this far, pushes harder against the boundaries of what current models comfortably predict. To keep the science grounded here, confirmed, coordinated bulk flow motion has been measured by multiple independent research teams using large galaxy catalogs and careful distance calculations. Still debated whether this flow's surprising strength points toward an unusually large underdense region, toward some other overlooked gravitational influence, or toward a genuine gap in how current models describe gravity across the largest cosmic scales. One recent analysis tracked this flow out to a distance of roughly 350 million light-years from Earth, and still found galaxies moving together in a shared direction at a speed noticeably higher than standard models comfortably allow. That is a distance large enough to include thousands of galaxies, all seemingly caught in the same gentle but persistent outward current, moving in step rather than scattering randomly the way pure chance would predict. Gravity pulling galaxies outward at unexpected speeds is strange enough on its own, but the story grows even stranger once statisticians got involved, running the actual numbers against standard cosmological predictions to see exactly how unlikely this entire situation truly is. Scientists have a specific way of measuring how surprising a result truly is, and it comes down to something called sigma. Think of sigma as a scale measuring how far a result strays from what pure random chance would normally produce. The higher the sigma number, the less likely the result happened by accident. A result reaching what scientists call 5 sigma is considered strong enough to officially declare a new discovery in physics, a threshold famously used when researchers confirmed the existence of the Higgs boson particle. 5 sigma roughly translates to odds of about 1 in a few million that the result happened purely by random chance. Now consider what happened when one research team modeled the KBC Void's size and depth against standard predictions for how underdense regions should form in a normally behaving universe. Their analysis found the void's characteristics disagreeing with standard predictions at a level exceeding 6 sigma, pushing past even the strict threshold normally used to confirm major new discoveries in physics. Picture flipping a coin and getting the exact same result 20 times in a row, technically possible under pure random chance, but so unlikely that any reasonable person would start suspecting the coin itself might be weighted unfairly. A 6 sigma statistical tension carries roughly that same flavor of improbability, a result so far outside expected randomness that something about the underlying assumptions likely needs correcting. This specific number came from comparing the void's measured size and density against large-scale computer simulations built using standard cosmological models, the same mathematical framework researchers use to successfully predict countless other features of the observable universe. Those simulations run through millions of possible universe configurations. Checking how often a void this large and this deep would naturally appear by pure chance alone. According to that analysis, it essentially should not. It is worth pausing here to explain what a statistical tension like this does and does not prove. It does not prove standard cosmology is wrong. Large, complex models, built from decades of accumulated evidence, rarely collapse from a single anomaly, even a striking one. What a result like this does prove is that something about the current picture remains incomplete. Whether that missing piece turns out to be a measurement error, an unusual but ultimately harmless statistical fluke, or a genuine crack pointing toward new physics waiting to be discovered. Some researchers studying this tension have proposed that standard cosmology's underlying math may need adjusting specifically for how quickly large voids can grow over cosmic time. Others maintain that improved data and larger galaxy surveys will eventually smooth this tension away, revealing it as a coincidence rather than a genuine crisis. To put that 6 sigma number in everyday terms, imagine a school where the average test score has stayed rock steady for 50 straight years. Then one class scores so far outside the normal range that teachers cannot explain it through luck. Something structural must be different. That is the position cosmologists find themselves in, searching for the structural reason behind a result their own models say should almost never happen. A 6 sigma mismatch sitting at the heart of our own cosmic neighborhood is not something scientists can casually dismiss. To understand exactly which rules this void seems to be breaking, we need to look directly at the rulebook itself, the standard model of cosmology that has successfully predicted the universe's behavior for decades, and see precisely where the friction begins. Every successful scientific model earns its trust the hard way, through decades of predictions that keep coming true. The standard model of cosmology, often called lambda CDM, has earned exactly that kind of trust. It successfully predicts the leftover glow from the Big Bang, the large-scale arrangement of galaxies across the universe, and the overall rate at which cosmic structures form and grow over billions of years. At its foundation, this model treats the early universe as starting from tiny, nearly uniform ripples in density, small variations that gradually grew larger over billions of years as gravity pulled matter together into galaxies, clusters, and the vast cosmic web connecting them all. Crucially, the model places strict limits on how large and how deep those ripples can realistically grow within the age of the universe we currently measure. Think of it like dough rising in an oven. Given a fixed amount of time and a fixed set of ingredients, dough can only rise so much before physics simply will not allow it to expand any further within that time frame. Standard cosmology places a similar kind of limit on cosmic structures. Given 13.8 billion years since the Big Bang, gravity has only had so much time to carve out empty regions and build up dense clusters, and that timeline sets a ceiling on how extreme those structures should realistically become. The KBC Void, according to several independent analyses, appears to bump directly against that ceiling, and in some calculations, breaks straight through it. A region this large, this empty, and this well confirmed should be exceptionally rare, if not essentially impossible, according to the standard timeline for how gravity slowly builds cosmic structure from those early tiny ripples. This creates a genuine friction point between observation and theory. The observation, a real, measured underdensity surrounding our galaxy, is well supported by multiple independent surveys using different telescopes and different wavelengths of light. The theory, standard cosmology's prediction for how large voids should realistically grow within cosmic history, struggles to comfortably accommodate a structure of this size showing up this close to home. Several possible resolutions have emerged from ongoing research. One possibility suggests the void's true size has been overestimated, and better data will eventually reveal a smaller, more theoretically comfortable structure, an idea supported by at least one recent study using a different measurement approach. Another possibility suggests gravity itself behaves slightly differently across extremely large scales than standard models currently assume, requiring a modification to the underlying physics rather than simply adjusting the void's measured size to stay balanced and precise. Confirmed, a real tension exists between the void's measured properties and standard cosmological predictions, published and discussed across multiple peer-reviewed papers. Still unresolved, whether that tension ultimately gets explained away through refined measurements, or whether it survives scrutiny and points toward a genuine gap in our understanding of how gravity and cosmic structure actually work. A rule book this well-tested rarely gets challenged lightly, yet here we are, standing inside a structure, seemingly daring cosmologists to reconsider it. To understand just how far this challenge extends, we need to zoom back out and examine the broader assumption at stake. The very idea that the universe should look roughly the same no matter which direction you happen to be looking. Modern cosmology rests on a quiet but powerful assumption, one so fundamental that most models simply build it in from the very beginning. Zoom out far enough, and the universe should look roughly uniform in every direction. No special favored locations, no unusual pockets that break the overall pattern. Scientists call this idea the cosmological principle, and it has held up remarkably well across decades of observation. This principle does not claim every small region looks identical up close. Clusters exist, gaps exist, individual neighborhoods vary just like neighborhoods vary within any city. What the principle claims is that once you average across large enough distances, spanning hundreds of millions of light years or more, those local differences should smooth out into a fairly consistent overall density, no matter which direction you happen to be measuring from. The KBC Void tests that assumption in an uncomfortable way, precisely because of its enormous scale. Small, ordinary gaps in cosmic structure are expected and unremarkable. A gap stretching close to 2 billion light-years, however, sits right at the edge of, and by some measurements beyond, the scale where the cosmological principle expects things to smooth out into a comfortable average. Picture stirring cream into coffee. Right after pouring, you can clearly see swirling patches, some darker, some lighter, mixed unevenly throughout the cup. Keep stirring, and eventually those patches blend into a single, even, uniform color throughout. Standard cosmology essentially argues the universe should resemble that fully stirred cup once you zoom out far enough. No leftover swirling patches, large enough to notice. A void this size resembles a swirl that refused to fully blend in, sitting stubbornly visible at a scale where the coffee should already look completely uniform. If further research eventually confirms that voids this large and this deep are more common throughout the universe than currently assumed, rather than existing as a rare fluke unique to our own location, that finding would carry real consequences. It would suggest the universe is less uniform on large scales than the cosmological principle currently assumes, which would ripple outward into recalculating countless other measurements that depend on that same underlying assumption. Researchers have not reached consensus on how seriously to treat this challenge. Some argue the KBC Void represents exactly the kind of rare, unlikely, but ultimately harmless statistical outlier that occasionally shows up in any sufficiently large universe, an unlucky roll of cosmic dice that happens to include our own galaxy. Others argue it represents genuine evidence that the standard picture needs meaningful revision, treating our region as a preview of a texture the entire universe might share more widely than assumed. Confirmed, the cosmological principle has passed extensive testing across most of the observable universe and remains the accepted starting point for the vast majority of cosmological work, still contested. Whether our own local void represents a rare exception proving the general rule, or an early crack revealing a larger pattern still hiding in plain sight, waiting for better telescopes and bigger surveys to fully expose it. To understand how scientists first started questioning whether the universe truly looks the same everywhere, we need to travel back to its very earliest moment, captured in a faint, ancient glow of light, still reaching Earth today from the dawn of everything. Long before galaxies existed, before stars ignited, before even atoms could form properly, the universe existed as a blisteringly hot, dense soup of particles and light. As that soup gradually expanded and cooled, roughly 380,000 years after the Big Bang, something remarkable happened. Light finally broke free, traveling outward in every direction for the very first time. That ancient light never fully disappeared. Stretched and cooled by billions of years of cosmic expansion, it now arrives at Earth as a faint microwave glow, detectable by specialized telescopes and satellites. Scientists call it the cosmic microwave background, and it functions almost like a baby photograph of the entire universe. Captured at the earliest possible moment, light could travel freely. This ancient glow carries incredible scientific value because it preserves tiny temperature variations, subtle differences of just a few parts in 100,000, scattered across the sky. Those tiny variations represent the original density ripples, the small clumps and gaps in matter that would eventually grow over billions of years into the galaxies, clusters, and voids scattered throughout today's universe, including the very structure surrounding our own galaxy. Picture examining a satellite photograph of a calm ocean surface at dawn before any waves have fully formed. Faint ripples barely visible on the surface hint at exactly where much larger waves will eventually build later in the day. The cosmic microwave background functions similarly, a snapshot of barely visible ripples that eventually grew into the massive cosmic structures scientists observe and measure today. Detailed satellite missions have mapped this ancient light with extraordinary precision, and the results have overwhelmingly confirmed core predictions of standard cosmology. The pattern of ripples matches theoretical expectations with remarkable accuracy across nearly the entire sky, providing some of the strongest supporting evidence available for the standard model as a whole. However, one particular patch of this ancient light has puzzled researchers for years, refusing to match expectations quite as cleanly as the rest of the sky. A specific region appears notably colder than the surrounding average, cold enough and large enough that its existence has sparked its own dedicated line of scientific investigation, one that connects directly back to the story of cosmic voids. Confirmed, the cosmic microwave background exists, has been measured with extraordinary precision, and provides powerful supporting evidence for the standard model of cosmology overall. Confirmed separately, one specific region within this ancient light behaves unusually compared to the rest of the sky. Still debated exactly what causes that unusual patch, and whether it connects meaningfully to the same kind of underdense structure surrounding our own galaxy. Multiple space missions have refined this ancient map over the years, each one sharper than the last, yet the cold spot has survived every upgrade. A false signal caused by faulty equipment or a processing error would likely fade or shift as instruments improved. Instead, mission after mission keeps finding the same chilled patch, sitting in the same location, reinforcing the idea that something physically real is producing the effect, rather than a glitch in the data. That unusual cold patch deserves its own closer look, because some researchers believe it might represent the fingerprint of an even larger void than the one we currently call home, an emptiness so vast it could be leaving a visible mark on light itself, stretched across billions of years and still detectable today. Somewhere within the ancient light mapping the earliest moments of the universe sits a patch unlike anything else in the sky. Scientists call it, quite simply, the cold spot, a region within the cosmic microwave background measuring noticeably colder than the surrounding average temperature. At first glance, a temperature difference this small might seem trivial. The variation involved is tiny, a fraction of a degree at most. But within the extremely precise, extremely uniform pattern scientists expect across this ancient light, Even a small deviation stands out sharply, especially when it covers a patch of sky far larger than ordinary statistical variation would predict. Picture a perfectly mixed bowl of soup, evenly warm throughout except for one noticeably cooler section near the edge, cool enough that a spoon dipped there feels distinctly different from anywhere else in the bowl. That is roughly the scale of anomaly researchers are dealing with here. Small in absolute terms, but strikingly out of place given how uniform the rest of the pattern behaves. Scientists have proposed several explanations for what might be causing this unusual chill. One leading idea connects directly back to cosmic voids. If a massive, underdense region sits directly along the path light travels on its way to Earth, that emptiness could subtly cool the light passing through it through a gravitational effect, involving how light loses tiny amounts of energy while climbing out of a shallow gravitational depression created by the missing matter. Researchers searching for a void large enough to fully explain the cold spot found something intriguing but not entirely conclusive. A genuinely enormous, underdense region, sometimes called the Eridanus supervoid, was identified roughly in the same direction as the cold spot in the sky. However, most analyses suggest this particular void, while impressively large, still falls short of being massive enough on its own to fully account for the entire temperature dip observed. This leaves researchers with an unresolved puzzle layered on top of an already unresolved puzzle. Perhaps a still undiscovered, even larger void exists in that same direction. One current surveys have not yet fully mapped. Perhaps multiple smaller, underdense regions combine together to produce the full effect. Or perhaps the cold spot's true cause lies somewhere else entirely, unrelated to any void at all, and its match with the Eridanus supervoid is simply an unlucky coincidence of overlapping sky positions. To stay careful and precise, confirmed, the cold spot is a real, measured, well-documented feature within the cosmic microwave background. Confirmed separately, a large underdense region does exist roughly along the same line of sight, still unresolved. Whether that specific void fully explains the temperature anomaly, partially explains it, or turns out to be unrelated to the cold spot's true underlying cause. What makes this puzzle so hard to close is distance itself. The Eridanus supervoid, if it truly exists at the scale needed to explain the cold spot, sits billions of light years farther away than the underdensity around our own galaxy, at a range where even the best current surveys struggle to gather enough data for a confident answer. Two separate emptinesses, one surrounding our galaxy directly, another possibly responsible for a cold imprint stretched across the earliest light in the universe. Whether these two mysteries are truly connected, or simply an eerie coincidence of cosmic geography, remains one of the most tantalizing open questions in modern astronomy, and it is far from the only giant hole in space, still waiting for a proper explanation. A cold patch in ancient light, a giant void sitting roughly in the same direction. Connecting those two facts sounds like an easy case to close, yet the scientific community remains genuinely divided on whether one truly causes the other. Understanding why requires looking closely at the physics linking emptiness to temperature and at just how much cooling a void this size can realistically produce. The mechanism itself is well understood and broadly accepted. Light traveling through a region with less matter than average experiences a subtle energy change tied to gravity, an effect physicists have modeled carefully for decades. As light climbs out of a shallow gravitational dip created by missing mass, it loses a tiny amount of energy, similar to how a ball loses speed rolling up a gentle slope, even if that slope never quite forms a proper hill. Slightly less energy in light translates to a slightly lower measured temperature by the time it reaches our telescopes. The disagreement is not about whether this effect exists. It clearly does, and it has been measured directly in smaller, well-confirmed voids elsewhere in the sky. The disagreement is about scale. Producing a cooling effect large enough to fully explain the cold spot requires a void significantly larger and significantly emptier than anything confirmed so far in that specific direction of the sky. Picture trying to explain a large dent in a car door using only a small pebble strike. The physics of pebbles causing dents is completely valid, well tested, and understood. The problem is whether a pebble alone, rather than something larger, could realistically produce a dent of that particular size. Researchers modeling the cold spot face exactly this kind of scale mismatch, confident in the mechanism but uncertain whether the known void is big enough to be the full explanation. Several research teams have proposed workarounds to close this gap. One idea suggests the void extends farther and deeper than current surveys have managed to detect, hidden partly by limitations in how far modern telescopes can reliably count faint, distant galaxies. Another idea suggests multiple smaller underdense regions, strung together roughly along the same line of sight, could combine their individual cooling effects into something large enough to match the observed anomaly. A separate camp of researchers argues the connection may be coincidental altogether. Statistically, across the entire sky, some patches of ancient light were always going to run colder than average, simply due to random variation, without any special underlying cause. Under this view, a large void happening to sit nearby in the same general direction could be an unlucky overlap rather than genuine cause and effect. Two unrelated mysteries that merely appear connected from Earth's specific vantage point. To stay precise, confirmed, voids can and do cool passing light through a well-understood gravitational mechanism. Confirmed separately, a large underdense region exists roughly along the same direction as the cold spot, still unresolved whether that specific void is large enough on its own to fully explain the anomaly, whether multiple voids combine to produce the effect, or whether the entire connection turns out to be coincidental. This tangled, unresolved mystery involving our own cosmic backyard raises an obvious question. If a void this size can spark this much scientific debate, what happens when researchers examine voids that dwarf our own entirely? The answer takes us to a discovery made decades earlier, almost by accident, in a completely different direction of the sky. Long before anyone had heard of the KBC Void, astronomers stumbled onto something even stranger, entirely by accident. In 1981, a researcher named Robert Kirshner was working with a small team, carefully measuring redshift, the stretching of light that reveals how fast and how far away a galaxy sits, across a wide section of sky. Their actual goal had nothing to do with searching for emptiness. They were simply trying to build a three-dimensional map of galaxy positions, piece by piece, the same slow and careful process used across many similar surveys at the time. Then, in the direction of a constellation called Boötis, the data suddenly went quiet. Galaxy after galaxy simply failed to appear where the map predicted they should be. At first, the team assumed something had gone wrong with their equipment or their calculations. Large, obvious gaps like this were not supposed to show up in ordinary survey data, but repeated checks confirmed the same result every time. A massive region of space, far larger than any random statistical gap should reasonably produce, contained almost nothing at all. Researchers initially nicknamed it the Great Nothing, before eventually settling on a more formal name, the Boötis Void, based on the constellation where it appeared. News of the discovery spread quickly through the scientific community, partly because of its sheer, almost unbelievable scale. To put that scale into perspective, one astronomer studying the void later offered a striking thought experiment. If our own Milky Way galaxy happened to sit at the very center of the Boötis Void, humanity might not have discovered that other galaxies existed at all until decades later than we actually did, since the nearest neighboring galaxies would sit so far away and appear so faint that even powerful telescopes would have struggled to detect them clearly. Unlike the KBC Void, which surrounds our own galaxy directly, the Boötis Void sits far away from Earth, its center located roughly 700 million light-years distant, deep enough into space that studying it required careful, painstaking distance measurements, rather than simply counting nearby galaxies. Its width stretches across roughly 330 million light-years, making it By some measurements, one of the largest confirmed voids ever directly identified through galaxy surveys. Confirmed clearly through decades of follow-up research, the KBC Void is real. Its emptiness has been independently verified by multiple survey teams since its original 1981 discovery, and its scale genuinely challenges expectations for how large a single underdense region should realistically grow. Modern surveys, equipped with far more powerful instruments than Kirshner's original team ever had access to, have since confirmed the void's boundaries with considerably greater precision, while still finding the same fundamental pattern that first startled researchers over 4 decades ago. Finding a structure this massive raises an obvious next question. If it truly contains almost nothing, what exactly is out there? As it turns out, follow-up surveys eventually found something unexpected hiding deep inside the emptiness, a small, scattered population of galaxies that took years of careful searching to properly uncover. Finding a massive void is only the beginning of the story. The far harder task is figuring out exactly how empty that void truly is, and that meant searching, patiently and carefully, for any galaxies that might still be hiding somewhere inside it. Early searches following the KBC Void's 1981 discovery turned up almost nothing at all, reinforcing just how dramatic the initial finding truly was. Then, gradually, over the following years, additional surveys, using improved equipment and more careful methods, began locating scattered galaxies buried deep within the supposed emptiness, one small cluster at a time. In 1987, a research team announced the discovery of 8 galaxies hidden within the void's boundaries. The following year, another team found 3 more. In 1989, a separate group located an additional 15 galaxies scattered through the region. Each discovery chipped away slightly at the void's reputation as pure emptiness, while simultaneously confirming just how genuinely sparse the region truly remained compared to typical space. By the time researchers had thoroughly combed through the area using every available survey technique, the total count settled at roughly 60 confirmed galaxies. Compare that number to a typical, ordinary region of similar size elsewhere in the universe, where astronomers would reasonably expect to find somewhere around 2,000 galaxies scattered throughout the same volume of space. Picture a massive sports stadium built to hold 2,000 fans, standing almost completely empty except for 60 scattered individuals sitting far apart from each other, each one isolated in their own section with vast stretches of empty seating stretching between them. That comparison captures roughly the scale of emptiness astronomers were dealing with once the final galaxy count came in. This discovery mattered scientifically for reasons beyond simple curiosity. Finding any galaxies at all, rather than truly zero, confirmed that voids are never perfectly, completely empty, reinforcing the same basic lesson learned from studying our own local underdense region. Even the most extreme cosmic gaps still contain scattered matter, just spread remarkably thin across an enormous volume. The KBC Void's galaxies also offered scientists a rare opportunity, a chance to study how galaxies form and evolve in near-total isolation, cut off from the dense clusters and busy neighborhoods where most galaxies typically grow. Researchers found that galaxies inside the void tended to be somewhat smaller and fainter on average, hinting that the surrounding emptiness might genuinely shape how a galaxy develops over billions of years, not just where it happens to sit. Confirmed through repeated independent surveys spanning multiple decades, roughly 60 galaxies exist within the KBC Void's boundaries, an extraordinarily low number for a region of this size. Still under active study, exactly how the void's extreme emptiness influenced the formation and development of the handful of galaxies that do exist there. Some researchers have proposed these isolated galaxies formed more slowly than average, starved of the nearby material that typically feeds galaxy growth in denser regions. Though confirming that idea properly requires studying each galaxy in far greater detail than current instruments comfortably allow, a void this size, containing this few galaxies, naturally raises the question of whether even larger, even emptier structures might exist somewhere else in the universe. still waiting to be found. It turns out an even bigger contender for that title has already been discovered, sitting even farther away, stretching the definition of cosmic emptiness even further. Somewhere beyond the Boötes Void, in a completely different direction of the sky, sits a structure that pushes the scale of cosmic emptiness even further. Astronomers call it, with refreshing directness, the giant void, and its dimensions rival, and by some measurements exceed, nearly everything else ever confirmed. Located in the constellation Canes Venatici, the giant void was first identified in 1988, spanning an estimated diameter between 300 and 400 megaparsecs, translating to roughly 1 to 1.3 billion light-years across. Its center sits approximately 1.5 billion light-years from Earth, placing it considerably farther away than either the KBC Void surrounding our own galaxy or the Boötes Void discovered nearly a decade earlier. For years after its discovery, the giant void held a reputation as the largest confirmed underdense structure known, edged out in official rankings only by a small handful of even larger candidates identified through later, more advanced surveys. Its sheer scale places it in rare company among cosmic structures, large enough that light itself needs well over 1 billion years just to cross from one edge to the other. Despite its name and its enormous size, the giant void follows the same familiar pattern established by every void studied so far. It is not truly empty. Inside its vast boundaries sit 17 confirmed galaxy clusters, concentrated together in a smaller, denser region, roughly 50 megaparsecs across near its center, similar to a small oasis of activity, surrounded by an overwhelming stretch of nearly barren space, extending outward in every direction. Researchers studying the giant void have paid particular attention to its possible connection with the cold spot anomaly discussed earlier. Some early hypotheses suggested this specific void might be massive enough and positioned correctly to produce the observed cooling effect on ancient light. More detailed follow-up analysis found the giant void does not correspond closely enough to the cold spot's exact position and scale to serve as a clean, complete explanation, leaving that particular mystery still unresolved even with this additional massive structure now firmly catalogued. What the giant void does confirm, alongside the KBC Void and the Boötes Void, is a pattern too consistent to dismiss as coincidence. Enormous, underdense regions, spanning hundreds of millions to over 1 billion light-years, appear scattered throughout the observable universe, far more frequently than early cosmological models comfortably predicted. 3 separate, independently confirmed examples, found using different survey techniques by different research teams, working decades apart, all point toward the same broader conclusion. Confirmed, the giant void exists. Its scale and rough position have been independently verified by multiple studies since its 1988 discovery. Still debated, exactly how such enormous voids form so consistently across cosmic history, and what their frequent appearance reveals about gaps in current models of how matter arranged itself following the Big Bang. Some researchers now suspect these 3 confirmed giants may represent only a fraction of similarly sized voids, still waiting to be properly mapped, hidden simply because current surveys have not yet covered enough of the sky in sufficient detail. 3 massive voids in 3 different directions of the sky is a striking pattern on its own. To understand exactly how striking, we need a way to compare these structures against something a human mind can genuinely grasp. Stacking cosmic emptiness against the largest, most familiar landmarks Earth itself has to offer. Numbers describing billions of light-years rarely stick in memory, no matter how carefully explained. What tends to stick instead are comparisons rooted in something familiar, something you could genuinely stand inside and feel the true scale of firsthand. So let's shrink these cosmic voids down to the size of something recognizable, Earth itself. Imagine shrinking the entire observable universe down until it fits neatly inside the borders of the continental United States, stretching from the Atlantic coast to the Pacific coast. On that shrunken scale, the KBC Void surrounding our own galaxy would stretch roughly the distance from New York City to somewhere well past Los Angeles, an entire coast-to-coast crossing just to cover one relatively modest cosmic void compared to its larger cousins. Now scale up to the Boötes Void, the massive structure discovered accidentally back in 1981. On that same shrunken map, its emptiness would stretch far beyond the borders of the continental United States entirely, spilling out past both coastlines into open ocean on either side, a single void too large to fit inside an entire country's worth of space. The giant void, larger still, would demand an even bigger comparison. Picture the entire surface of the Pacific Ocean, the largest ocean on Earth, covering roughly 1/3 of the planet's total surface area. Scaled down using the same universe-sized model, the giant void's emptiness would rival crossing that entire ocean, coast to coast, just to reach its far edge. Try one more comparison, using Earth's largest desert instead of its largest ocean. The Sahara Desert stretches across roughly 3.5 million square miles, an area so vast it could comfortably swallow the entire continental United States within its borders. Even that legendary expanse of sand and heat shrinks down to an almost trivial dot once placed beside any of these cosmic voids on a properly scaled map. These comparisons matter for more than simple wonder. They help translate an abstract number, however large, into something the human mind can genuinely process and feel. A distance measured in billions of light years remains meaningless without context. A distance compared to crossing an ocean or driving coast to coast across an entire country several times over suddenly becomes something close to comprehensible, even if the true scale still stretches far beyond anything achievable in an actual human lifetime. What makes these comparisons even more remarkable is remembering what fills these enormous spaces. Not simply water, or sand, or open highway, but the near total absence of galaxies, stars, and light across distances, dwarfing anything found on Earth's entire surface. A commercial airplane crossing the Pacific takes roughly 12 hours to reach the far shore. Crossing the giant void at the speed of light, the fastest anything can travel, still takes well over 1 billion years, a timescale that makes even the longest ocean flight feel instantaneous by comparison. Understanding just how empty that emptiness truly is naturally raises a deeper physics question. What if the emptiness itself is not simply a passive gap in matter, but a clue pointing toward gravity, behaving differently across scales this extreme? Every explanation examined so far treats gravity as fixed and unchanging, the same reliable force at every scale, from a falling apple to an entire supercluster of galaxies. A small but serious group of physicists has begun questioning that assumption directly, proposing that gravity itself might behave slightly differently once you stretch it across truly enormous cosmic distances. This idea traces back to an entirely different puzzle first noticed decades ago, involving individual galaxies rather than giant voids. Stars near the outer edges of spiral galaxies orbit far faster than standard gravity, based solely on visible matter, predicts they should. The most common explanation invokes dark matter, an invisible substance providing the extra gravitational pull needed to hold everything together properly. A smaller group of researchers proposed an alternative explanation instead. Rather than adding invisible matter, what if the actual law of gravity itself changes slightly at extremely low accelerations, the kind of gentle, barely detectable pull found at the outer edges of galaxies and across the vast, nearly empty stretches between them? This alternative approach became known as modified gravity, and one specific version, called MOND, has spent decades earning both praise and criticism from the physics community. Picture a thermostat that behaves perfectly normally across most everyday temperatures, but starts responding slightly differently once conditions become extremely cold, colder than anything most households ever experience. Modified gravity theories propose something structurally similar: ordinary gravity behaving exactly as expected in strong, everyday conditions, like holding planets in orbit around stars, but shifting subtly under the extraordinarily weak gravitational conditions found across vast cosmic voids and galaxy outskirts. Several research teams have specifically applied modified gravity models to the KBC Void and the broader Hubble tension puzzle, finding that these alternative theories can sometimes produce large voids more naturally and more easily than standard gravity comfortably allows. Under some of these models, a void this large forming within the current age of the universe becomes far less statistically surprising than the 6 sigma tension calculated under standard assumptions. It is essential to stay balanced here, because modified gravity remains a genuinely contested idea within physics, not a settled alternative ready to replace the standard model. These theories successfully explain certain galaxy rotation patterns with remarkable precision, yet they consistently struggle to fully match observations at the scale of galaxy clusters and the earliest light from the cosmic microwave background, areas where standard dark matter-based models continue performing more reliably overall. Confirmed, modified gravity models exist, have been rigorously tested for decades, and successfully explain some specific observations better than standard approaches. Still unresolved and actively contested whether these models can be extended successfully enough to explain cosmology as a whole, including structures like the KBC Void, without breaking accuracy in other areas where standard gravity currently succeeds. Physicists on both sides of this debate generally agree on one point: that resolving it will likely take years of additional testing rather than a single decisive experiment settling the matter overnight. If gravity truly behaves differently across the largest cosmic scales, an entirely separate line of evidence becomes especially important to examine closely: the strange, coordinated motion of galaxies drifting through and around these underdense regions at speeds that continue to defy easy explanation. Galaxies rarely sit still, but the sheer coordination of their movement across our local universe has become a genuine puzzle in its own right. Rather than drifting randomly in every direction, huge numbers of galaxies across an enormous stretch of space appear to be moving together, roughly in the same general direction, at speeds higher than standard cosmological models comfortably predict. Scientists refer to this coordinated motion as bulk flow, and measuring it accurately requires painstaking work. Researchers track the precise distance and velocity of thousands of individual galaxies scattered across a wide volume of space, then mathematically combine those individual measurements into a single average motion, revealing whether galaxies in a given region are drifting together as a group or moving independently in random direction. One especially detailed study applied this method using an enormous galaxy catalogue, carefully tracking motion out to a distance of roughly 350 million light-years from Earth. Rather than fading out or leveling off at that distance, as most standard models would predict, the measured bulk flow remained unusually strong, and in some analyses appeared to keep increasing the farther out researchers measured. Picture releasing a handful of leaves onto the surface of a wide, calm lake, expecting them to drift apart slowly in every direction as gentle currents scatter them randomly. Instead, imagine watching all those leaves drift steadily together toward one particular shore, moving faster the farther they travel, rather than slower. That unexpected, sustained, coordinated motion is roughly the behavior astronomers have documented among galaxies across this section of the local universe. This bulk flow connects directly back to the void story already explored. A large underdense region sitting near our galaxy could plausibly generate exactly this kind of coordinated outward drift, as nearby galaxies feel a persistent gravitational pull toward denser regions surrounding the emptiness. The trouble is scale. The measured bulk flow appears considerably stronger and extends notably farther than most models built around the currently accepted void size can comfortably explain on their own. Several competing explanations remain on the table. Some researchers argue the void itself must be larger or positioned differently than current estimates suggest, capable of generating the full observed flow once properly modeled. Others propose that additional, still undiscovered massive structures somewhere nearby might be contributing extra gravitational pull alongside the void's effect. A smaller group continues exploring whether modified gravity theories might explain the excess flow more naturally than any combination of standard structures possibly could. Confirmed through multiple independent research teams, galaxies across this section of the local universe are moving together in a coordinated pattern, at a strength exceeding typical predictions from standard cosmological models. Still unresolved, the precise combination of causes responsible for that unexpectedly strong and unexpectedly persistent motion. Researchers continue refining their catalogues, adding newly measured galaxies year after year, hoping a larger, more complete sample will finally reveal whether the flow eventually tapers off at some greater distance or continues defying expectations even farther out than currently measured. A universe full of unexplained motion naturally invites questions about what else might be hiding, unseen, exerting influence from the shadows. That question leads directly toward one of astronomy's most persistent and mysterious subjects, the invisible substance believed to make up the vast majority of all matter in the cosmos. Every void story eventually runs into the same enormous, unknown, dark matter, the mysterious substance believed to account for roughly a quarter of everything in the entire universe, yet never once directly detected by any instrument built so far. Understanding whether our local void behaves as expected requires seriously considering how this invisible material factors into the entire picture. Dark matter does not emit light, absorb light, or interact with ordinary matter in any way scientists can directly observe. Its presence is inferred entirely through gravity, through the way it influences the motion of galaxies, the bending of light around massive clusters, and the overall structure of the cosmic web connecting galaxies together across the universe. Essentially, scientists know dark matter exists because of what it does, not because anyone has ever actually seen it. This creates a genuine complication for studying voids properly. Every density measurement discussed so far, every galaxy count, every survey mapping emptiness across the sky, technically measures only visible, ordinary matter, the stars, gas, and galaxies telescopes can actually detect. If dark matter distributes itself differently than ordinary matter across large cosmic voids, actual density measurements could be significantly off, even while the visible galaxy counts remain perfectly accurate. Picture judging how crowded an entire city truly is by counting only the cars parked visibly on the street, while completely ignoring an enormous number of people walking, biking, or riding underground subways completely out of sight. Your visible count might be entirely accurate for cars specifically, yet still miss the true overall picture of how populated that city actually is. Something similar could be happening with dark matter hiding within our supposedly empty cosmic void. Some researchers have proposed that our local void, despite appearing significantly underdense in visible galaxies, might contain a more typical amount of dark matter, effectively softening its true gravitational effect compared to what visible galaxy counts alone would suggest. Under this scenario, the void's impact on local expansion measurements and the surrounding bulk flow would be considerably smaller than models based purely on visible matter currently predict. Other researchers push back against this idea, pointing out that most large-scale computer simulations already account for dark matter clustering alongside ordinary matter throughout cosmic history, and those simulations still struggle to naturally produce a void this large and this persistent. Under this competing view, dark matter alone cannot fully resolve the tension between our observed void and standard cosmological predictions. Confirmed, dark matter exists. Its gravitational influence has been measured and confirmed through multiple independent lines of evidence spanning decades of research. Still genuinely uncertain exactly how dark matter distributes itself within and around large cosmic voids like our own, and how significantly that distribution might change scientists' current understanding of the void's true depth and influence. Resolving this specific question will likely require combining traditional galaxy counts with entirely separate techniques, such as measuring how light bends slightly while passing near unseen concentrations of mass, a method that does not depend on visible galaxies at all. An invisible substance potentially reshaping our entire understanding of cosmic emptiness is exactly the kind of problem that demands better tools and bigger data. Fortunately, astronomers are already deploying exactly that, a new generation of survey instruments built specifically to map the universe with a level of precision and scale no previous project has ever achieved. Every mystery explored so far shares one common limitation. The data, however impressive, remains incomplete. Existing surveys have mapped enormous stretches of sky, but enormous gaps and blind spots still remain, hiding potential answers just beyond the reach of current instruments. A new generation of telescopes and survey projects has been specifically built to close that gap. These next-generation projects share a common ambition, mapping galaxies across the sky with a scale and precision far beyond anything achieved by earlier surveys. Rather than sampling small patches of sky and extrapolating outward, these newer projects aim to catalogue tens of millions of individual galaxies directly, building three-dimensional maps detailed enough to resolve subtle structures that older surveys could only estimate roughly. Picture the difference between an old, hand-drawn map of a coastline, sketched from a distance using rough estimates, compared to a modern satellite photograph capturing every inlet, every peninsula, and every small island in precise detail. That leap in precision is roughly what these newer surveys offer, compared to the studies that first identified the KBC Void, the Botez Void, and the Giant Void decades earlier. This new level of detail matters enormously for resolving the ongoing debates already explored, determining the true size of our local void, rather than relying on estimates that sometimes disagree by a factor of 10, depending on the measurement technique used, requires exactly this kind of precise, comprehensive galaxy count. The same applies to confirming or ruling out a genuine connection between the cold spot and any specific underdense region hiding nearby. Researchers are especially focused on studying voids themselves as valuable scientific tools, rather than simply obstacles or curiosities. A void's size, shape, and internal structure carries encoded information about how matter clustered together in the early universe, information that complements what scientists already learn from studying dense galaxy clusters directly. Some researchers now argue that voids deserve equal attention alongside clusters when testing and refining cosmological models going forward. This growing focus has already produced results. Newer surveys have successfully mapped tens of millions of galaxies and quasars, creating three-dimensional maps far more detailed than anything available even a few years earlier. And these maps are actively being used to search for signs that dark energy, the mysterious force driving cosmic expansion, might behave differently than previously assumed. Results from this ongoing work continue arriving, with major findings expected within the next few years as data collection continues. Confirmed, multiple major survey projects are currently active, collecting galaxy data at a scale far exceeding anything available when the KBC Void, the Botez Void, or the Giant Void were originally discovered. Still ahead, the detailed analysis needed to definitively settle exactly how large, how deep, and how influential our local underdense region truly turns out to be. Researchers involved in these projects have described the coming years as a genuine turning point, the first time in the history of cosmology that enough data will finally exist to test these long-standing void-related questions with real statistical confidence. Two specific projects stand at the center of this new push, each built with slightly different strengths. Together aiming to chart a scale of the universe no single instrument could achieve entirely alone. Two major projects currently lead the charge toward mapping the universe with unprecedented precision, each approaching the challenge from a slightly different angle, together forming one of the most ambitious efforts in the history of observational astronomy. The first, called the Dark Energy Spectroscopic Instrument, operates from a mountaintop observatory in Arizona using thousands of tiny robotic arms working in perfect coordination to capture the light spectrum of individual galaxies, one after another, across enormous stretches of sky. Each robotic arm can be precisely aimed at a single galaxy, allowing the instrument to measure thousands of galaxies simultaneously during a single observation session, rather than one painstaking measurement at a time. This project recently completed its originally planned 5-year mission, and the results exceeded expectations by a wide margin. Rather than the roughly 34 million galaxies and quasars originally targeted, the completed survey successfully mapped more than 47 million objects, producing the most detailed 3-dimensional map of the universe ever created, stretching back across 11 billion years of cosmic history. Given how well the project performed, researchers have already extended operations, aiming to expand coverage even further and push the total count past 60 million objects before the mission eventually concludes. The second major project, a European space telescope, approaches the challenge from an entirely different vantage point, observing from space itself rather than from the ground. Positioned beyond the interference of Earth's atmosphere, this space-based observatory captures extraordinarily sharp, wide-field images across vast sections of sky, tracing the subtle gravitational bending of light caused by massive structures, a technique that reveals not just where galaxies sit, but how dark matter itself clusters and spreads throughout the surrounding cosmic web. Picture 2 different search teams looking for a lost object in a vast, dark forest. One team walks carefully through the forest itself, systematically tagging every tree and clearing they encounter along the way. The other team flies high overhead in an aircraft, capturing a wide, detailed aerial view, revealing the forest's overall shape and structure from a completely different angle. Combining both approaches produces a far more complete picture than either team could achieve working entirely alone. Both projects share a common core mission: better understanding dark energy, the mysterious force believed to be driving the universe's ever-accelerating expansion. Yet, as a direct side effect of that broader goal, both projects are also producing exactly the kind of extraordinarily detailed density maps needed to finally resolve the size, shape, and true influence of underdense regions like the one surrounding our own galaxy. Early results from these projects have already produced surprising hints, suggesting dark energy itself might not behave as a perfectly constant force throughout cosmic history. A finding that, if fully confirmed through continued analysis, would represent a major shift in how scientists understand the universe's ultimate fate. Full results addressing these deeper questions remain forthcoming as researchers continue processing the enormous datasets already collected. Confirmed. Both projects are actively operating, have already produced groundbreaking, unprecedented datasets, and continue expanding their coverage of the sky. Still ahead, the detailed follow-up analysis needed to determine exactly what these enormous new maps reveal about the true size and significance of our own local cosmic void. With better maps finally within reach, a deeper question comes into focus. What does living inside a confirmed underdense region actually mean, not just for measuring the universe's expansion rate, but for how humanity understands its overall place within the cosmos? Every measurement humanity has ever made about the universe was taken from exactly one location: Earth, sitting inside our own solar system, inside our own galaxy, inside this specific underdense region of space. That single fixed vantage point carries consequences worth examining carefully, because a telescope can only ever show us the universe as it appears from right here. Cosmologists have long assumed, reasonably, that our specific location represents a fairly typical spot within the universe, unremarkable in any statistically significant way. Confirming a large, well-documented void surrounding our own galaxy directly challenges that assumption, at least locally, raising an important question about how much that atypical location might be quietly distorting some of our most fundamental measurements. Consider how this might affect calculating something as basic as the age of the universe. That calculation depends heavily on accurately measuring the expansion rate, exactly the same measurement complicated by the Hubble tension already explored throughout this story. If our local void genuinely distorts nearby expansion measurements, even slightly, every calculation depending on those numbers inherits a small amount of that same underlying uncertainty. Picture trying to accurately judge the average height of everyone in an entire country, but only ever measuring people from one specific, unusually tall neighborhood. Your calculated average might turn out reasonably close to correct despite the skewed sample, or it might turn out to be significantly and misleadingly off, depending entirely on how unusual that specific neighborhood truly is compared to the country as a whole. Cosmologists face an analogous challenge, needing to carefully account for exactly how unusual our own cosmic neighborhood might be before fully trusting certain calculations drawn from local data. This challenge extends beyond simply calculating numbers correctly. It touches something more fundamental about how confidently scientists can generalize from local observations to statements about the entire universe. Much of modern cosmology rests on the working assumption that our corner of space behaves as a reasonably fair, representative sample of the whole. A confirmed, significant local void forces researchers to more carefully examine exactly where that assumption holds strong and where it potentially begins breaking down. Importantly, this challenge has not overturned cosmology as a whole, nor should it be mistaken for evidence that the entire field rests on shaky ground. Countless other predictions from standard cosmological models continue matching observations with remarkable precision across the vast majority of the sky. The local void represents a specific, contained challenge, requiring careful, targeted adjustment, not a wholesale collapse of decades of accumulated scientific understanding. Confirmed, our galaxy's specific location within a documented underdense region genuinely complicates certain local cosmological measurements in ways scientists must carefully account for, still being actively worked out. Exactly how much adjustment is needed, and precisely which calculations require correction versus which ones remain reliable, regardless of our unusual local position. Many astronomers now treat correcting for this local bias as a standard, expected step in careful analysis, similar to how a scientist automatically accounts for instrument calibration before trusting any final result. If our own location within the universe carries this much scientific weight, an intriguing question naturally follows. What would the universe look like from somewhere else entirely? From a hypothetical vantage point sitting inside one of the universe's genuinely crowded, dense regions, instead of our own comparatively empty neighborhood. Every measurement explored throughout this story assumes one fixed, unchangeable perspective, Earth's own specific location within this particular underdense region of space. It is worth pausing to genuinely imagine an alternative, a civilization studying the cosmos from an entirely different vantage point, one situated inside a dense, crowded region of the universe, rather than our comparatively sparse cosmic neighborhood. Picture an intelligent observer studying the sky from somewhere deep inside a massive galaxy cluster, surrounded on every side by countless neighboring galaxies, dense filaments of matter, and none of the enormous stretches of near emptiness surrounding our own location. Their night sky would likely appear dramatically busier than ours, packed with visibly nearby galaxies rather than scattered thinly across enormous, mostly empty distances. More importantly, for this story, their local measurements of cosmic expansion would likely tell a noticeably different story than ours. Without an underdense region nearby, generating the kind of extra outward drift explored earlier in this series, that hypothetical observer's local expansion rate calculations might align far more closely with measurements taken from the ancient cosmic microwave background, potentially eliminating, or at least substantially reducing, their own version of the Hubble tension entirely. This thought experiment carries genuine scientific weight, not just poetic interest. Several research teams have specifically run computer simulations testing exactly this scenario, calculating what expansion measurements would likely look like from various different hypothetical locations scattered throughout a simulated universe. These simulations generally confirm that an observer's specific location, particularly whether they happen to sit inside an unusually dense or unusually sparse region, can meaningfully shift their calculated expansion rate compared to the true, overall cosmic average. Picture two people standing on opposite sides of a large, crowded stadium, each trying to estimate the average density of the crowd around them. Someone standing near a heavily packed entrance gate would likely estimate a much higher average crowd density than someone standing near a wide-open exit walkway on the opposite side, even though both are technically measuring the exact same overall stadium. Cosmic observers scattered throughout the universe likely face an analogous challenge, each potentially reaching a slightly different conclusion about the universe's true expansion rate, depending entirely on their own specific local surroundings. This idea does not suggest the universe behaves differently depending on who observes it, or that some fundamental law of physics changes from place to place. The underlying physics remains identical everywhere. What changes is simply the local environment surrounding each specific observer and how that local environment subtly influences certain nearby measurements before those measurements get generalized into broader conclusions about the cosmos as a whole. Confirmed through computer modeling, an observer's specific cosmic location can measurably influence certain local expansion calculations, an effect well supported by simulation-based research. Still purely hypothetical, whether any other observers actually exist elsewhere in the universe to experience this effect firsthand, since that question extends into territory current science cannot yet answer with any confidence. Thinking through hypothetical observers elsewhere naturally circles back to a much more grounded, immediate question about our own specific situation here on Earth. Is our galaxy's location within this void a rare, unlucky cosmic outlier? Or is the wider universe stranger and less uniform than most scientists have assumed for decades? Every void, every measurement, and every unresolved tension explored throughout this story eventually circles back to one central, unavoidable question. Is Earth's cosmic neighborhood simply an unlucky statistical fluke, one rare, unusual patch scattered among an otherwise ordinary universe? Or does our situation hint at something larger and more fundamental still waiting to be properly understood? The statistical fluke explanation carries genuine scientific weight and should not be dismissed lightly. Given an incomprehensibly vast universe, containing trillions of galaxies scattered across unimaginable distances, some regions were always statistically destined to land on the unusual, sparse end of the distribution, purely through random chance alone. Under this view, our galaxy simply happened to end up in one of those rare, unusually empty pockets. An unlikely but not impossible outcome given enough available space and enough time for randomness to play out. The alternative explanation carries equally serious scientific weight, though it points toward more unsettling implications. If voids this large turn out to be genuinely common throughout the universe, rather than existing as one rare exception unique to our own location, that finding would suggest something more fundamental needs revising within current cosmological models, whether that means adjusting how quickly structure is allowed to form, reconsidering the role of dark matter and dark energy, or seriously entertaining a genuine modification to gravity itself across the largest possible scales. Picture flipping a coin and getting heads 10 times in a row. One perfectly reasonable explanation is simple: unlikely luck, a genuinely rare but entirely possible outcome, given enough total coin flips happening somewhere. A second, competing explanation suggests the coin itself might be subtly weighted, biased, in a way that makes that streak far more likely than pure random chance alone would predict. Both explanations remain scientifically valid starting points. Only closer, more careful examination of the coin itself, or in this case, the underlying structure of the universe, can ultimately determine which explanation truly fits. Ongoing survey work, including the newly expanded projects already discussed, aims to directly settle exactly this question. If upcoming, more comprehensive surveys reveal several other galaxies scattered throughout the universe, also sitting inside comparably large, comparably empty voids, that pattern would strongly favor the idea that something structural, rather than simple random chance, deserves serious reconsideration. If our own void continues appearing as a clear, singular outlier compared to everywhere else surveyed, the simpler, statistical fluke explanation gains correspondingly stronger support. Neither outcome would be considered a failure for cosmology as a scientific field. Science regularly advances precisely through resolving exactly this kind of open tension, gradually replacing genuine uncertainty with increasingly confident, well-tested answers as better data becomes available over time. What currently remains genuinely unresolved is which specific direction the eventual answer will ultimately point toward. Confirmed, this question remains a legitimate, actively pursued open problem within contemporary cosmology, discussed seriously across ongoing research rather than dismissed as settled either way. Still unknown, whether our local cosmic neighborhood ultimately turns out to be a rare, unlucky exception, or an early, revealing preview of a texture shared more broadly throughout the wider universe. Wherever this particular question eventually leads, it connects to something even larger, already lurking beneath the entire story. A serious, ongoing debate among physicists about whether one of history's most successful and trusted scientific theories might genuinely need updating. Few scientific theories have earned as much trust as Einstein's general relativity, the framework describing gravity as the natural curving and bending of space and time itself around massive objects. For over a century, this theory has successfully predicted an extraordinary range of phenomena, from the bending of starlight around the sun to the precise behavior of orbiting planets to the recently confirmed existence of gravitational waves rippling through the fabric of the universe itself. Yet even a theory this successful faces genuine, serious open questions once applied to the very largest cosmic scales explored throughout this story. The persistent Hubble tension, the surprising strength of bulk flow motion among nearby galaxies, and the statistically unlikely size of our local cosmic void together form a cluster of related puzzles that some physicists believe general relativity, paired with the standard cosmological model built around it, may not currently explain as cleanly as once assumed. This does not mean serious physicists expect Einstein's equations to be proven wrong in any dramatic headline-grabbing sense. Far more likely, according to most researchers actively working on this problem, would be a careful refinement or extension, similar to how Einstein's own theory itself refined and extended Isaac Newton's earlier understanding of gravity without completely discarding everything Newton had correctly established centuries earlier. Picture a highly detailed, extremely accurate map of a familiar city, one that has correctly guided travelers for over 100 years without a single serious complaint. Then imagine explorers venture into a newly discovered district on the far outskirts of that same city, an area the original mapmakers never actually had the tools or technology to properly survey. Finding that the map runs slightly inaccurate specifically within that newly explored district would not invalidate the excellent, reliable work already done everywhere else across the rest of the city. It would simply mean that specific unexplored edge needs updating with better information. Several concrete research paths are currently being pursued to address this challenge properly. Some researchers continue refining standard cosmology itself, searching for previously overlooked effects, like the local void's influence discussed throughout this story, that might fully resolve the tension without requiring any fundamental changes to gravity at all. Others continue developing and testing modified gravity theories, hoping to find a version flexible enough to correctly explain both galaxy-scale observations and universe-scale cosmology simultaneously, something no current modified theory has yet fully achieved. Still others focus on searching for genuinely new physics entirely, some undiscovered particle, field, or force capable of resolving the tension in a way nobody has yet properly considered. It is important to stay grounded and realistic here. No single explanation currently commands overwhelming consensus support across the physics community. The debate remains genuinely open, actively contested at conferences, and argued over in published research on a near constant, ongoing basis. Exactly the kind of healthy scientific uncertainty that eventually, given enough time and enough data, tends to produce real, lasting progress. Confirmed, general relativity remains extraordinarily well tested and successful across the vast majority of situations where it has ever been carefully checked. Still, genuinely open. Whether the specific puzzles explored throughout this story, the void, the tension, the bulk flow, ultimately require a meaningful refinement to that otherwise remarkably successful theory. Resolving this debate, whichever direction it eventually points, would carry consequences reaching far beyond academic curiosity alone. Discovering the true nature and true edge of our own cosmic void would reshape scientific understanding in ways touching nearly every corner of modern physics. Every thread explored throughout this journey eventually leads back to one specific, concrete goal, precisely determining the true size, depth, and boundary of the underdense region surrounding our own galaxy. Reaching that specific answer would carry consequences reaching far beyond simply satisfying scientific curiosity about our cosmic address. Consider what a precise, fully confirmed measurement would mean for the Hubble tension specifically. If the void turns out large and deep enough to fully account for the observed mismatch between local and distant expansion measurements, that single finding would essentially resolve one of modern cosmology's most persistent decade-spanning open problems, allowing scientists to finally settle on a single, universally agreed expansion rate for the entire universe. Alternatively, if the void turns out too small to fully explain the tension, as some newer studies using different measurement techniques have already suggested, that finding would push researchers to seriously consider other explanations instead, whether involving modified gravity, undiscovered particles, or some entirely different physics nobody has yet properly proposed. Either outcome moves science meaningfully forward, replacing genuine uncertainty with a clearer, better supported answer. Picture a detective working a genuinely difficult case, with several credible suspects still under serious consideration. Definitively ruling out even one suspect through solid, careful evidence represents real progress towards solving the case, regardless of whether that particular suspect turns out to be guilty or innocent. Precisely measuring our local void functions, similarly, narrowing down the realistic possibilities and helping researchers concentrate their future efforts more efficiently on whichever explanations remain most credible and best supported by the evidence. Beyond directly resolving the Hubble tension itself, a precise void measurement would also meaningfully improve scientists' broader understanding of how cosmic structure forms and evolves throughout billions of years of history. Voids, alongside dense galaxy clusters, serve as a genuine natural laboratory for testing exactly how gravity behaves across the largest scales the universe has to offer. A well-measured void provides real, concrete data that any future theory of gravity, whether that remains standard general relativity or some meaningfully modified version, will eventually need to successfully explain. This resolution would also carry real, practical benefits reaching beyond pure theory alone. Astronomers routinely use assumptions about cosmic expansion and structure to calculate distances, ages, and future trajectories for countless objects scattered throughout the universe. A more precise, better confirmed understanding of our local cosmic environment would improve the underlying accuracy of calculations, spanning an enormous range of ongoing and future astronomical research, from studying distant galaxies to searching for potentially habitable planets. Confirmed, Precisely resolving our void's true properties would meaningfully advance multiple major, currently unresolved areas of physics and cosmology simultaneously. Still ahead, the actual data collection and detailed analysis needed to finally deliver that long-awaited, precise answer. Work that is already actively underway through the major survey projects already discussed throughout this journey. Many researchers involved expect at least partial answers within the next several years, as newly collected data continues working its way through careful analysis and peer review. All of this evidence, every measurement, every debate, and every unresolved tension eventually circles back toward one final, sweeping question worth sitting with directly, a question reaching beyond cosmology itself and into something closer to humanity's own place within the vast, still mysterious universe surrounding us. Every discovery explored throughout this journey eventually points toward one final, deeply human question, hiding quietly beneath all the technical measurements, statistical tensions, and competing scientific theories examined so far. What does it genuinely mean that Earth and everything humanity has ever known or discovered sits inside an unusually empty pocket of the universe? Consider the practical consequences first. A galaxy sitting inside a genuinely sparse cosmic neighborhood simply has fewer nearby galactic neighbors than a more typical galaxy elsewhere might enjoy. Fewer nearby galaxies statistically means fewer nearby stars, fewer nearby planetary systems, and correspondingly, fewer potential opportunities for other forms of life to have independently emerged somewhere reasonably close to our own cosmic backyard, at least compared to a hypothetical galaxy sitting instead within one of the universe's genuinely dense, crowded regions. This does not mean life becomes impossible, or even necessarily rare, purely as a direct consequence of our local emptiness. Our own solar system, our own planet, and our own emergence as a curious, questioning species all happened successfully despite, or perhaps in some ways because of, this particular cosmic address. What changes is simply the surrounding statistical landscape, the raw number of reasonably nearby cosmic neighborhoods where similar stories might have independently unfolded elsewhere. Picture a small, quiet town built far out on the edge of civilization, surrounded by wide-open countryside rather than dense, closely packed neighboring towns. People in that quiet town can absolutely still live full, meaningful lives, build lasting communities, and accomplish extraordinary things entirely on their own. What differs is simply how far they would need to travel before encountering their nearest neighbors, and correspondingly, how many neighboring communities exist within any given reasonable traveling distance from their own front door. Some researchers have begun seriously exploring whether this kind of cosmic address might carry measurable consequences for the broader search for extraterrestrial life. A civilization emerging inside an unusually sparse cosmic region would, statistically, have fewer nearby galaxies worth searching for signals within, and any signals they did eventually send outward would need to travel correspondingly farther before reaching another sufficiently dense, potentially inhabited region capable of receiving and recognizing them. It is essential to treat this specific idea with appropriate scientific caution. The connection between local cosmic density and the broader likelihood of nearby life remains almost entirely speculative at this stage, resting on reasonable extrapolation rather than any direct, confirmed evidence currently available. No study has definitively proven that sparse cosmic regions meaningfully reduce the actual chances of life emerging somewhere within them. What remains firmly confirmed, grounded in years of careful, independently verified research, is this: Earth sits inside a real, measurable, unusually underdense region of the universe, a structure astronomers have been carefully studying, debating, and refining their understanding of for well over a decade now. That structure continues actively reshaping how scientists calculate the universe's expansion rate, its age, and quite possibly the fundamental laws of gravity governing everything within it. The next generation of telescopes and survey projects, already actively collecting data as this very story comes to a close, promises answers that could finally resolve many of the open questions explored throughout this entire journey. Until those answers fully arrive, Earth remains exactly where it has always been, quietly suspended inside its own strange, still mysterious pocket of cosmic silence, waiting patiently for humanity to finally map its true edges.